Hello everyone. In this video, we are going to see the topic isoparametric element, then types of isoparametric element, then two-dimensional elasticity problems. Okay. So in unit number 6, finite element method for the subject structural analysis 2. So isoparametric element for the analysis of structural problem of the complex shapes involving curved boundaries or surface, simple triangular or rectangular element are no longer sufficient. Okay, so if the structures involving the complex shapes that are having the curved boundaries or surface, the simple triangle or rectangular elements are no longer sufficient. So this has led to the development of element of having arbitrary shape known as isoparametric element. Okay, so this concept was brought by Teich and BMIN. Okay, of mapping the regular, triangular and rectangular element in natural coordinate system to arbitrary shape in global coordinate system. Okay, so concept of mapping is in isoparametric element. So this is the parent element and this is mapped in the global coordinate system. Okay, so in parent element it is in national coordinate system. So plane triangle is here. Here it is mapped in the global coordinate system. Okay, so these are some examples. Okay, now we'll see the types of isoparametric element. There are three subclasses of isoparametric element. Okay, first one is isoparametric element, second one is subparametric element, third one is superparametric element. Okay, so we'll see the first one, that is isoparametric element. Okay, so if you see in the figure, so here the circle nodes are used for defining the geometry and the rectangle nodes are used for defining the displacement. Okay, so in this figure if you see, the number of nodes used to define the geometry as well as number of nodes used to define the displacement are equal. Okay, are equal or same. So it is called as isoparametric element. If the same number of elements is used to define the geometry as well as displacement, the element is called as isoparametric element. Okay, so next one is subparametric element. Okay, now in this figure you see the number of nodes used to for defining displacement is more than the number of nodes used to define the geometry. So in such case it is called as subparametric element, that is the element in which less number of nodes is used to define the geometry compared to the number of nodes used to define the displacement. Okay, the element is called as subparametric element. Okay, so it is quite clear from the figure. And last one is superparametric element. Okay, again we'll observe the figure. In the figure, the number of nodes used for defining geometry is less than number of nodes used for defining the displacement. That is, number of nodes used for defining the displacement is more than that of the node used for defining the geometry. Okay, so the superparametric elements are the element in which less number of nodes is used to define the displacement compared to the number of nodes used to define the geometry. So such elements are called as superparametric element. Okay. Now we'll see the advantage of isoparametric element. What are the different advantages of the isoparametric element? So first one is shape function are used for defining the geometry as well as displacement. Okay, so this is the first advantage. So due to the shape function are used for defining the geometry as well as the displacement. Second, suitable for structure having the complex shape or the curved boundaries. The structure having the complex shape or the curved boundaries for these isoparametric elements are very much suitable. So due to that, what happened? The next advantage is it increases the accuracy of the result. It increases the accuracy of the result. And fourth one is satisfy the Pascal triangles and require less computational work. So it satisfies the Pascal triangle and required less computational work. So these are the certain advantages of the isoparametric element. Okay. Now this is also very important term, that is two-dimensional elasticity problem. Okay. So what are those? The first one is the plane stress problem. Second one is plane strain problem, and third one is axis symmetric problem. Okay, so what are the plane stress problem? Okay. So here, two-dimensional elasticity problem under the following conditions are considered as a plane stress problem. So what are the conditions? One dimensional is very small as compared to the other two dimension. One dimension is very small as compared to the other two dimension. For example, if you take an example of rectangular plate, so here two dimension, that is length and breadth, is more as compared to the thickness. So here the thickness is very small as compared to the length and the width. So this is the first condition. Second, the load is acting on the body are in plane perpendicular to the thickness of the body. Whatever the load is acting on the body are in the plane perpendicular to the thickness of the body. That is z-axis. So load is uniformly distributed over the thickness. The load is distributed over the thickness. And third one, the stresses in the small direction, that is in z-axis, okay, must be 0. So the stresses must be 0. So these are the condition of the plane stress problem. So example of slab also we can take, okay, as the thickness of slab is less as compared to that of the length and width. Okay. So this was regarding the plane stress problem. Now we'll see the plane strain problem. Now here two-dimensional elasticity problem under the following conditions are considered as plane strain problem. What are the conditions? So the first condition is one dimension is long as compared to the other two dimensions. Okay. So if you see the example of plane strain problem, the example is, okay, a retaining wall is there, okay, dam is there, bridge is there, okay. Then we can say pipeline is there. So in that what happened, one dimension is more as compared to the other two dimensions. For example of the retaining wall, the length is more as compared to the width and height. Okay. So here example are retaining wall, dam, bridges. Okay. So here external force is perpendicular to the z-axis. So external force is perpendicular to z-axis. That means the longitudinal axis here it is nothing but z-axis. The strain in the longer direction, okay, strain in the longer direction must be 0. That means sigma z, it should be not equal to 0, but epsilon zz, and this dabba xz and dabba yz, it should be equal to 0. Okay. Then we'll see the next, that is axis symmetrical element. So also known as ring type element. Okay. Use full for analysis of problems such as cylindrical, storage tank, shaft and rocket nozzle. Axis symmetrical elements are generated by rotating a line or a curve about the axis. So if you see, this is one dimensional axis symmetrical element, which is conical frustum. So second is a ring with a triangular cross section, which is a two-dimensional. So here we have seen that it is also known as a ring type element. Okay. So these axis symmetrical element are generated by rotating a line, okay, about the axis. Okay. So this axis, and about that axis it is rotated. Okay. So the example are conical frustum, it is example of one dimensional, and the example two dimensional is ring with a triangular cross section. So So thank you for watching this video.